Now, we'll talk more about simple machines when we get to a point where we can talk about what they do. But in a general broad case, all of the four simple machines do the same thing. They exchange force for distance. They allow an increase of force at the expense of distance, or a decrease of force in order to commit to more distance. If you don't know what I mean by that, most of you didn't jump to the second floor today. Most of you took the stairs. And this is because the jump to the second floor requires the application of a lot more force than the requirement of going up the stairs. The difference is that the jump to the second floor would be a shorter distance than going up the stairs. The stairs are an inclined plane. They exchanged force for distance. You apply less force over a longer distance to do the same amount of work as jumping to the second floor would do. All of these do the same thing. If you've ever had to jack up your car before to change a tire, if you have a old style pump jack, well, you only need to raise the car this big, but you have to apply a lot of force to lift the car. You'll apply less force at the end of the jack handle, but it's going to be over a lot of pumps, which means a very long distance. You don't have to apply as much force as the force necessary to lift the car, but you have to do so over a greater distance. All of these do the same thing. They allow for the exchange of force for distance. Same thing here and here, although people don't tend to see that an inclined plane is a screw or how a screw exchanges force for distance. But if you take an inclined plane, which is just something that looks like that, it's a wedge. It's also an inclined plane if you set it on the ground. If you roll it up, then what you get at the end is a screw. So a screw only has to travel this far, but has to be twisted a very long distance in order for it to go a very short distance into the piece of wood or into the wall or whatever it is. But a screw is just an inclined plane that's been rolled up along one of its axes. And again, it does the same thing that an inclined plane would do.
What is that circle thing?
It's me saying that you're going to spin it. Sorry, that's all I got. So today, we're going to talk about the inclined plane. And we've already done a problem similar to this, so I want to kind of call your mind to that problem. A couple of days ago, I put the calculator on the book. Not sure you remember. So I put the calculator on the ramp. It is 272 grams, and it clearly did not move. It stayed there. So your job was to draw a free body diagram representing the calculator on the ramp. What I'm going to ask you to find today is the frictional force and the normal force that act on the calculator. Inclined planes are the most prevalent problem in all of physics. They are used consistently from this point in the year till the end. So we use inclined planes as a means of trying to see if you fully understand force, work, energy, and momentum. So it's going to come up a lot more than this. Your mastery of the inclined plane is probably going to determine whether you can master the course or not, even though it's really not that complicated. But an incredible number of students miss stupid things. And I hate to say the word stupid, but they are, because they fail to take down the details. So I'm going to ask you politely, and I'm going to stop. So you start with your dot to indicate where the object is. This is the mass of the calculator. And we're going to decide from the beginning whether this is a Newton's first law problem or a Newton's second law problem. What do you think? Clearly, first law problem, the calculator did not slide or move at all. So it's a first law problem. Free body diagram requires that I go through my list of things here. And I had a conversation with a student yesterday that was almost infuriating at the inability to apply these simple rules. They are simple. I really can't make them much simpler. So we're going to start with the force of gravity. Was there a force of gravity acting on the calculator? Yes. Do you have any choice as to how to draw this arrow? No. So no choice. You draw a downward arrow. That's it. You can put a W there or an MG there. I don't care. All right, we're done with the conservative forces. Now we move on to the contact forces. Is the calculator in contact with any surface? Yes. Again, do you have a choice on how to draw this arrow? Well, apparently you do. According to the student, there's some options. Would you draw it this way or this way? Right. The surface can only push. It can't pull. It's a pushing force. So it can only push outwards away from itself. So there's no way the ramp pulls the calculator down. Luckily, that student is not in here to hear me berate that choice. Is there a cable, rope, string? So there's no tension force. Does this look balanced to you? If it doesn't look balanced and you know that it is, you need to continue to look at the resistive forces. Is there likely a resistive force acting on the object? Is it friction? Friction has the definition of the force to try and prevent one surface from sliding past another. So the surface of the calculator sliding past the book seems to fit that description. That also means, though, that that force can only be in this direction, along the ramp, either up the ramp or down the ramp. Those are the only two options. So here you do have to make a choice, a small one. It's an A-B choice. So it's either going to be choose the arrow on the L side or the arrow on the R side. Which side makes the most sense to balance these two forces? Okay, so I'm feeling like this class isn't having the same troubles, but remember, I only hear the people that actually are saying things to me. Now, it's bound to come up. Mr. Shelton, why did you draw the F smaller than the N? It's bound to come up. But remember, you're trying to strike balance. So I looked at how long that was, the portion of this force that goes to the left. That's what I looked at, the portion of that force that goes to the left. And I looked to make sure the portion of this force that went to the right was the same. For the same reason why my normal force is less than the weight. I knew there would be two pulling forces upwards. I knew that from experience. You might not have that experience, which is why sometimes yours won't be perfect. That's okay. But I did look to see that these two contribute to pulling upwards on the book, and they must compare favorably with this one pulling downwards on the book. I'm trying to make sure or strike a bit of a balance between up, down, left, and right, because net force equals 0. You should be doing the same. And I know that none of that discussion is up here. That's what your notes are for. All right, so I think we have successfully captured all of the forces acting on the object. We good to move on? So for the last few minutes, I've been talking about the fact that there is a desire to have balance. And I looked at up and down and left and right balance. That's because I was, in my head, projecting a coordinate system, an up, down, left, right coordinate system, the more natural one we tend to use. And if we were to use this coordinate system, we could successfully find the information out that I am asking. The problem is that I've not used my priorities on how to set up my coordinate system. And because of that, I've left two of these forces to need to be resolved, meaning trig on those two forces. However, and I'm trying not to make a big deal about this, but you should make a big deal about this in your notes. Friction and normal have to be perpendicular to each other. They have to be. Friction will always be perpendicular to normal force. I should say that different because you guys are smarter than that. Friction will always be perpendicular to the normal force that created it. There, that's a little bit better because I want to make sure if we have two normal forces, we are being consistent. Normal force creates friction, but those two, that pair, have to be perpendicular to each other. You know, that has farther reaching consequences than you are probably capable of imagining right now. So let me help you imagine things. In the near future, we're going to write those things out, aren't we? So I can tell if you're really paying attention by just looking at those. If friction and normal appear in the same one, you did it wrong. You see what I'm saying, right? Friction and normal have to be perpendicular to each other, so they will never be in the same one of those. They'll always be in opposite ones of those. Always. They have to be. So, back to work here. I think we've already talked about this. There is a better way to set up our coordinate system. But herein lies the problem. We're going to set up the coordinate system to be aligned with probably the normal force and the frictional force. Like so. Many students get to this moment and really don't know what to do about the angle of the ramp. Because the ramp was at an angle. And they're not sure where that goes here. So what I'm going to talk about now is an effective way for you to figure out where it goes. Okay? And that's what our next few seconds is about. I want you to remember that at one time, we started out with the axes aligned with the weight. Like that, right? Would you agree that the horizontal one is lined up with the horizontal line there that goes with the ramp? In order for us to turn the axes to line up with the ramp, we have to turn this axis, theta, right? That many degrees it has to be turned. So that's what I'm going to do. I'm going to turn this one theta degrees to get it to line up with the ramp. This is our x axis. So this is the one that I put an X here and an X here. Now, you can't turn that one without also turning the y-axis. So the y-axis has to also turn the same number of degrees, theta. Which means this side has to go away from the weight, theta degrees. So, theta has to be the angle between the weight and whatever axis is lined up with the normal force. Theta has to be the angle between the weight and whatever axis is lined up with the normal force. Yeah. Theta has to be the angle lined up with the weight and whatever axis is lined up with the normal force. Now, you have only a few things left to do here, and one of them is to make sure that you have determined what direction you're going to call positive and what direction is negative and what direction is X and what direction is Y. I kind of handled the X and Y for you, but positive, negative, good for you guys with Y. Now, this one doesn't matter. Do you want left to be positive or right to be positive? It kind of freaks people out to have to make this decision. They like the things to be the same as they've always been in their other classes. But if there was no friction, what direction would the box slide?
Down.
So when you consider the possibilities, don't get so attached to negative and positive. Because if I make this the negative direction and the box does slide, that means your acceleration's negative for going down the ramp. I would always encourage you to consider putting the positive direction in the direction of likely motion. Now, this object didn't move, but if it were to slide, wouldn't it slide this way? You will be happier in your future if you put the positive direction in the direction of likely motion. I promise, especially the problem I'm going to give you tonight. Now, I'm not saying change what you did. I'm just saying in your notes, give yourself that direction. You'll always be happier if you make your positive direction the direction of motion, or the likely direction of motion. Okay, I had a lot of students do this next part wrong, which is why I'm going to come by and check your work now. You have to wrap a triangle around the angle. So this is on you. I want you to wrap a triangle around the angle to break the weight up into its components. It's the only off-axis force is the weight. So please draw in the triangle that you would use to break up the weight. And I do want to see what you do here. When you're drawing this, the weight has become your hypotenuse. Remember, it is the one you're trying to break up into components. So it's the hypotenuse of your triangle. The most likely thing people do, because they're so consistent, is they want to make this their triangle. But that's not how we do it. We are taking and creating two vectors that are perpendicular to each other that make up the weight. We're actually trying to figure out how far down here does the weight go along the y-axis, and how far along here does it go on the x-axis. So to do that, we wrap our triangle here and we stop and make a right angle turn and go this way. The right angle's there. That way, this becomes the opposite side, this becomes the adjacent side, and this becomes the hypotenuse. It's like everything has been shifted that number of degrees. If we can't really easily rotate that, but if you just like rotate your paper, you can see it looking straight, everything kind of lining up along X and Y. It's because the whole thing is tilted, that's an issue. Also, trust me when I say, some of you who have drawn your pictures, they look great, but you didn't make this a right angle between the two axes. Your two axes are kind of askew. That will come back to hurt you later when you're trying to visualize what's happening. So do a better job of trying to make those two things at a right angle to each other.
When we're drawing this like on test or something, can we just tilt it like the whole thing?
Yeah. Yeah, there was at least two people in the room who just did that. They just drew them. Once they got the things down, they just tilted the whole thing, to whatever number of degrees. Okay, so keeping this up and trying to finish on time, mg is the length of the hypotenuse. So I don't want to do the trig anymore, meaning I want you to kind of come to grips with this has to be mg cosine theta, and this has to be mg sine theta. The cosine goes with the adjacent side, and the sine goes with the opposite side. Now, I can do sine theta equals opposite over hypotenuse, and cosine theta equals adjacent over hypotenuse to prove that. But I want to get to a point where I don't have to any longer. So I just want to be able to say, if it's on the adjacent side, it gets cosine, and if it's on the opposite side, it gets the sine. You're breaking this up into its pieces. And sine and cosine are the size of the pieces. So this whole side is mg sine theta. It's the part that points in the x direction. And this whole side is mg cosine theta, and it's the part that points in the y direction. Are we okay with that before I go on? Because, and let me say this outright, it's probably always going to be like that. Every inclined plane is going to be the same. If you put something on an inclined plane, those are going to be the components you're going to get. So weight in the x direction is almost always going to be mg sine theta unless something bizarre is going on. They do something weird to the problem. And weight in the y direction is probably almost always going to be mg cosine theta. AP doesn't want you to memorize this. They want you to be able to figure it out. But you don't have time to figure it out on multiple choice tests. And there'll be inclined planes on a multiple choice test. Count on these two things. And if you're taking notes, this pulls it down the ramp. This is responsible for pulling it down the ramp. And you guys are smart. Sine gets bigger when the angle gets bigger. So it gets pulled down the ramp faster, the steeper the ramp is. Look, there's not a person in here who doesn't understand that. You go to the water park, if you want to go on the scary rides, you go on the ones at the steepest ramps. They're fastest. You go to the kiddie pond, all the ramps are lame. You want steep and fast. I assume, unless maybe you like lame. On the other hand, how much it presses into the surface decreases as the angle gets bigger. You get less pressure in the surface, the steeper it is. Imagine you go all the way to 90 degrees, you don't have to touch the wall at all. You just fall straight down. Now, there's more to this, but very little more. What I mean by that is we can solve our problem now. This whole thing had a problem in the beginning, and so now we can solve that problem. I want you to find the frictional force and the normal force. Net force in the x direction is going to give us one of those. Positive x is mg sine theta. Negative x was friction. That has to equal 0. You now have an expression for the frictional force. Into the ramp, net force in the y direction. Positive y is normal. Negative y is mg cosine theta. Those have to equal 0. So if I want you to find an expression for the friction or normal force, you could do so. So I give you, 40 degrees, and the calculator is 272 grams. You can figure out what those two forces are. Now, I know I only have minutes left, so I want you to repeat this tonight. Here's what I want you to do to repeat it. I want you to imagine I have a very long 100-meter ramp. And it's only inclined 25 degrees. And I've got a box that I'm going to drop right at the top of the ramp. 2 kilograms. This part's going to be hard. Friction is 10% of the normal force. Friction is 10% of the normal force. 0.1 times the normal force. I would like to know how long it takes for the box to go down the ramp. And how fast is it going at the bottom? We've not done a problem like this yet. This is your first one. I'm going to tell you right now how to do it. This is a Newton's second law problem. You can tell the box is going to accelerate as it slides down the ramp. Now, what you need to do is understand that forces can only tell you the size of an individual force or an acceleration, which should translate to you guys that you have to do net force first to figure out the acceleration. Hint, net force is down the ramp, x direction. Second, once you get the acceleration, you've got a motion problem. Once you find the acceleration, you know it started from rest, has to travel 100 meters, and will have an acceleration that you will get from the force problem. I don't know if you can do this or not. Give it 15 minutes of your time tonight. I will post the numerical answers. If you can't do it in 15 minutes, shut it down and stop. Okay? But if you're catching on to this, you should be able to do it in about 15 minutes. Any question about what I'm asking you to do this evening? All right. Again, I will post the numerical answers as an announcement, probably after the NHS meeting. In the same direction as perpendicular to the ramp. And you would have to make your mass in kilograms to do this correctly. Good to keep going? Yes, ma'am.
Why is the angle of like the weight 25 degrees?
Well, I gave the angle of the ramp 25 degrees. Is that what you're asking?
Yeah, but yeah, so like why would you make the weight?
Information. Friction is 10% of the normal force. This problem wouldn't be stated like this. I would never say friction is 10% of the normal force. I would say the coefficient of friction is 0.1. Right? Letting you know that the only difference between this problem and what's on your test is I would use the words coefficient of friction. So if I said the coefficient of friction is 0.1, that's saying that friction is 10% of the normal force. Many people think this looks easier. They know how to deal with this, but I'm letting you know, saying the same thing to say the coefficient of friction is 0.1. I was going to do this as a demo, but I think, let's see if we can work our way through this. And I want to be clear, you guys, when we're starting these, let's start each problem from scratch. So I have an object on the ramp. I'm going to reduce it to a dot. And I'm going to start by saying, all right, it's got weight acting downwards. There's a normal force acting perpendicular to the ramp. So that has to be upwards and a bit to an angle, like so. So that, and then I have a frictional force, because they tell me that friction is 10% of the normal force. So the frictional force has to be pretty small, and it has to be directed along the ramp and likely upwards. I say likely, I want to be really clear, friction is in the opposite direction of motion. I think the box is going to slide down the ramp, so I'm going to put friction up the ramp. Now, it's at this moment that if you have been saying I didn't know where to get started, where you should ask a question about how did I come up with any of these things that are here? Okay, so I'm going to apply a coordinate system, and I'm going to use the first priority of my coordinate system, which is to line it up with the direction of the acceleration, which I believe is going to be down the ramp. So I'm going to effectively make this the positive x direction. I think you will always be happiest if you make the positive x direction the direction of your acceleration. So be, I don't know what the word I want to use here is, but be obvious about it. Tell yourself, I think it's going to accelerate down the ramp. I'm going to make positive down the ramp. That makes this the negative x direction. That forces me to make my y direction in the direction of the normal force. And that creates the condition where this has to be 25 degrees. Are we good so far? All right. I saw on a lot of papers yesterday, people drawing that triangle and making this a right angle. That's wrong. It's 1,000% wrong. Well, no, you can't be 1,000% wrong, but it's 100% wrong. This has to be the hypotenuse of whatever triangle you're drawing. So the right angle has got to be opposite that side, bless you. So I'm going to draw my triangle so that the right angle is on the axis right there. That's the way it should be drawn. And this side is the opposite side, so it's going to be mg sine theta, and this side is mg cosine theta. Any question about that? Are you sure? So all of you who said I didn't know where to get started, this is why I'm stopping here and making sure each step is something that you can do for the next one, which will be tomorrow on a quiz. Yes, ma'am.
Is mass in kilograms or grams?
I gave mass in kilograms, I believe.
If the angle of the rim is 25.
Okay, so I'm not sure I fully understand your question, but let me try, okay? Let me see how I want to do this. Does that help everybody else? Yes, sir?
So no matter what, in either a first law or second law problem, weight still equals mass and gravity?
Yes. Weight is always mg.
Okay, thank you.
So if I look at this now, I see net force in the x direction and net force in the y direction. I was careful to make sure that I lined up my x direction with the direction of the acceleration. That was on purpose. By doing that, I am forcing the net force in the y direction to be 0 and the net force in the x direction to be ma. Remember, this is a Newton's second law problem because the box accelerates. You are purposefully selecting x to be the direction of the acceleration so that the acceleration all goes in one direction. If you don't do that, you have to have acceleration in the x direction here and acceleration in the y direction here, and that's going to make your problem impossible for you to do because you don't know how much it gets split. So we force our problem to be one-dimensional so that we handle one dimension at a time here and one dimension at a time there. Now, I'm just asking you to follow directions, but if you follow these directions, this forces the x direction to be the direction of the acceleration. There are two forces in the x direction. There is mg sine theta, and there is friction. Oh, it doesn't equal 0, it equals ma there. Now there are two forces in the y direction, normal force and mg cosine theta. Now, we have applied Newton's laws, and it produced for us two relationships. That's all Newton's laws can do anyways, is produce two relationships like this. It's what we do now that determines whether we can get at what we were asked, which was to figure out the acceleration. Yes, ma'am?
When writing the net force, do you always like the positive number?
That doesn't matter, as long as you're careful to make sure you select their direction. So right now we'd be at an impasse if we didn't have more information because I have an unknown here. I can't figure out the acceleration without knowing the frictional force. I mean, I have m, I have theta, I have g, so I could plug that in, but I need the frictional force. But we were given, do we have a way of getting the normal force? It appears that we do. Normal force is equal to mg cosine theta. Do we know m? Do we know g?
Yep.
And do we know theta?
Yep.
So it appears to me that we can find out what the normal force is.
4.53.
If that's true, the normal force is 10%. The frictional force is 10% of the normal force. That's 0.1 times the normal force. So if you're saying the normal force is 4.53, then the frictional force has to be 0.453 newtons. That has to be the size of the frictional force. That is 10% of the normal force. So now I have mg times the sine of 25 minus 0.453 equals ma. You can plug what you need in here and figure out what the acceleration is. And by the way, the acceleration I think comes out to be 3.3 meters per second squared.
Is it fine if we do 3.32?
I would keep lots of decimal places between steps.
Okay.
Any questions about this? Yep.
When you were making the equations, how did you know like where to put the normal force and the frictional force like in it? Like I know that the friction like goes with the x because it's on that axis, and same with the normal force with the y. But how do you know to like subtract the mg cosine theta from the normal, but then in the other one to subtract the mg sine theta, like subtract the friction from that?
Okay. When I indicated that this way was the positive x direction, and I looked at this arrow and noticed it was pointed in the same direction, then I know this has to be in the x direction because it's along the x-axis. Even though I drew it down here, it's technically in this direction on the box. So I intentionally made it positive because it's in the positive direction. The frictional force points in the negative direction, so I am intentionally making it negative. Does that make sense? I'm not subtracting it. I'm adding up all the forces and taking their direction into account.
That makes more sense.
Okay. Yes, ma'am. 10%?
Oh, okay.
Is that okay?
Yeah.
We all right so far? Look, this is like test question material here, so that's why I'm asking. Let me tell you that to figure out the acceleration, and then did a motion problem. All right, so here's my box. And we've already identified forces on it. I'm not going to spend a ton of time trying to make this perfect, but I want to make it as clear as possible that there is a force this way on the box that's perpendicular to the ramp, and a force that is straight down. Good so far? So if we start out with the belief that horizontal lines up with the weight, like if we try to make a coordinate system that is lined up with the weight, and that would mean that the x direction would be perfectly horizontal, right? This is how we would start, but we want to turn the horizontal direction so it's lined up with the ramp, right? So to do that, I'm going to turn the x direction and tip it downwards on this side 25 degrees. Correct? Mm-hmm. But now I have to move the y direction too, because y has to be perpendicular to x. How many degrees am I going to be turning the y direction?
25 degrees.
So I'm going to turn it up at the top here 25 degrees, which is going to line it up with the normal force. But that also means to do that, I had to turn it away from the weight 25 degrees. Does that make sense? Yeah. So that's why this 25 degrees goes between the weight and whatever is lined up with the y-axis. We'll still do part of it. We used the force information demo. So look at what I gave you. We slid the box across the floor. I say we, but it was just me. So box, that's not a box. Box. It was heaved. I don't know how fast I threw it, but it went 5 meters along the floor and came to a final velocity of 0. It had a displacement of 5 meters, a time of 1.18 seconds, and a final velocity of 0. And I asked what the coefficient of friction was. Now, first, you have to understand, force is only about acceleration or forces. This is none of those things. However, I think you might be able to figure out acceleration here. This problem is done in the reverse of what we just did. In this problem, we have motion information. You could probably use it to do a force problem. So find the acceleration first. And then draw your free body diagram on the box. Some of you are going to mess this up, but this one's easier than the last question. But for whatever reason, every year I do this, people mess this up. So keep in mind, this problem begins the moment it leaves my hands and is sliding on the floor. So I'm no longer pushing the box. I threw it. The moment it left my hands is when this problem begins. So I am not actively pushing the box in this problem. Now, find the acceleration first. No one should have difficulty with that. Grab your favorite motion equation and, bang this one out. Hey, RJ, what'd you get for the acceleration? Oh, all right. Thinking 30 more seconds till I will call anybody out for the acceleration. But RJ, you got it? Negative 7.18. Anybody else get negative 7.18? I'm hearing a variety of numbers, but I have at least several people who support negative 7.18. I would have used delta x equals v final t minus 1/2 a t squared. That would be 5 equals 0 minus 1/2 a times 1.18 squared. That's 10 divided by 1.18 squared. Is that right? And that gives us 7? Seems pretty reasonable to me. So go ahead and give me that with a decimal attached, RJ. 7 point what?
1.
And it's negative. I'm sure it worked out to be negative. That shouldn't surprise us. The box was slowing down. Any questions about that? No. I will point out that the friction problem that's being presented here begins with a motion problem. But I can only get this number if I know friction and normal force. It's the only way I can get that number. So if I want to find out this problem, I need to find out what the frictional force was and what the normal force was. That sounds like something that force can solve for us. It can find out the value of a force. So you need to find out the value of the forces here, which means a free body diagram to get started. How many forces act on the box? Let's start at the top. Is there a gravitational force acting on the box? So did you draw that downwards? Is there any contact forces acting on the box? Is it in contact with the surface?
Yes.
What surface is that?
Floor.
The floor. So I should draw an upward force. And I'm thinking the upward force is balanced with the downward force. Did the box accelerate up or down? Not as it slid on the ground. Is there any pulling forces on the box? Any cables, ropes attached to the box? Are there any other surfaces in contact with the box? What? The normal force is from the floor. So move on to resistive forces. Is there any resistive force acting on the box? Friction. What direction should I draw it? To the left. So this way? Have I identified all the forces, or are there more? Okay. There is a desire for people to put a force to the right here, but there isn't one. The forces have to be unbalanced. The box was slowing down. I am expecting them to be unbalanced. It doesn't require a force for the box to move forwards. It was already moving forwards when we started looking at it. That's because I pushed it first. But now the floor is slowing it down. This is the forces acting on the box. I'm going to apply a coordinate system that is lined up with the direction of the acceleration. Now the acceleration is negative. That means it's slowing down. I know that that acceleration has to be due to the fact that the box is being accelerated by friction. I'm going to make the negative x direction in the direction of the frictional force because the acceleration came out to be negative. And normal. Now, the rest of this, again, you'll notice this is all just prescriptive. If you notice, we're doing the exact same thing we've been doing. Right, set of steps the same. So net force in the x direction equals ma. Net force in the y direction equals 0. Normal minus weight equals 0. Is that good? So normal equals mg. Negative friction equals ma. There's only one force in the x direction, it's friction. Do you have a way of finding the frictional force and the normal force now? I believe you do. Now, the actual numerical answer doesn't matter much to me, but it matters to you guys. And I think you should do the math on this. You should figure out what mu is. Should you use 9.8 or 10 here? We should use 9.8. We did the experiment. But I was fudging all the numbers. I don't know if it's 5 kilograms. But interestingly enough, I want to ask you guys, if you are really looking at this, does it matter what the box weighed? If friction equaled MA, and it does, and if weight equals mg, and it does the mass of the box matter?
No.
It didn't in the last problem either, but I didn't want to point that out yet. We're going to find that if you do your work without putting your numbers in, you'll find that many times stuff that's given doesn't actually matter. Which is why on a test, if I just say I throw a box across the floor, oftentimes on the test, students will say, Mr. Shelton, you didn't give us the mass of the box. And I'll just look at them and say, you're right. Deal with that. It's because I know the future of the problem, the mass wouldn't matter. So sometimes it might be better for you not to put the numbers in early, put the numbers in at the end. So you see the things that matter and the things that don't. Here, the mass didn't matter. What'd you get, like 0.7?
0.73, yeah.
Yeah, it's pretty high coefficient of friction. But I mean, that's what it was. You saw it. To be honest with you, the coefficient of friction is actually higher than that. The box didn't slide the full 5 meters. It was in the air for the first meter because I couldn't actually just lay it on the floor and push it. Not terrible, though.